continents collide. In a sense, mountains can contest with each other. Unlike in Middle-earth, in real life, rock isn't animated, but it can move over time, pressed by tectonic forces, moving what used to be seabed continental crust up to the loftiest heights of the tallest mountains on Earth, like Mount Everest here. The process is called orogeny, mountain building. Any kind of event that forms mountains, including subduction-related processes, and other processes too, but a mountain-forming event is an orogeny. The tallest mountains on Earth are orogenic results from continent-continent collisions. K2, the second highest peak on Earth. Both this and Mount Everest are part of a band of mountains called the Himalayas. And these are a collisional mountain belt, formed when the continental crust of, in this case, India, slowly slammed into the southern edge of the Asian continental plate. The result is the continental crust is granitic on both sides, India and Asia, and it can't subduct either under the other for long. So instead what happens is when two continents collide, they create these vast mountain ranges, the tallest on Earth. The Himalayas are produced from the slow collision of India with Asia about 25 million years ago, stretched out over time. It wasn't instant. And it resulted in the buckling of the Asian continental crust and the forcing of the crust to move out of the way, essentially, buckling as India itself warped as it runs into Asia. And you can look at this Google Earth map, and you can look at the satellite image, and you can see it. You can see India is one big mass, roughly triangular mass of rock, continental crustal plate. And you can look and see the mountain range piling up in front of it. As it moved north, it bulldozed Asia ahead of it, as it too was bulldozed up into high mountain peaks. Look on both sides. Look on the western side of India and the eastern side. Western side toward Pakistan, eastern side toward Bangladesh. And you can look at, without even being a geologist, you can see that the land itself is tortured. It's been warped and shifted as India has plowed north. You can see the clear track that it took and the land that warped around it on both sides, as the Himalayan range and the Himalayan plateau behind it rose as a result. The island continent of India ran into Asia. It started its journey about 100 million years ago, when it split off from part of Africa, when Africa used to be in a different position as part of the Gondwana continent of the southern hemisphere. India and Madagascar split off. India traveled much further, though, and over about 50 million years or so traversed the Indian Ocean, pushed along by tectonic forces, until about 55 million years ago when it ran up into Asia and pile-drived ahead this massive mountain range that would continue and is continuing to grow even today, warping the continental landmass around it and establishing India as now a fixed part of the larger Asian landmass. And as you can see here in this really nice animation developed by C.R. Scotese of the PaleoMap project, showing over the past 100 million years the progress of India as it moves originally as part of the Gondwana continent, moving across the Indian Ocean, and then, and you can see as it runs into Asia, all the landmass moves around it as it continues to move north, compressing inner parts of the Asian continent to drive up the Himalayan plateau behind the tallest mountain range on Earth. You can see here, and I'm going to repeat it a few times as I talk about this, the progress of India as it moves and hits Asia. You're seeing a very, what we think, very generic, stereotypical kind of continent-continent collision. The forces driving the ocean plate will drive sometimes a microcontinent or a small continental plate until it runs up against another continental plate. This is often how continents grow. Continents are hard to destroy as such. They can erode down to wave base. Mountains can erode down to be flat. But it actually is not very easy to completely destroy continental crust. In practice, what happens is continental slabs accumulate. They accrue against each other as they slam into each other. In this case, India slamming into Asia. And notice that the subduction zone, which is what brought it there, the ocean crust on both sides of India was moving north as part of a subduction zone under Asia. So Asia already at that point, in the southern part of Asia at that time, had a growing subduction-related mountain range. And then India adds to that. But notice what happens when the Indian continental plate runs up to the Asian plate. It at first follows the course of the subduction zone, but then its own buoyancy asserts, and it can only be pushed so far, and then it begins to lock into place as part of the lower part of this continental crustal mass. The descending ocean plate that was there before continues descending, but the subduction zone there is now off. Now, during an orogenic event, when you have a mountain building event going on like this, where continents are colliding, you can achieve geologic conditions inside those mountains, down within in the rock, that normally are not encountered. You have continental crust slamming at tectonic force against another continent. And the continental rock is not particularly hot. It's just the normal, what we call geothermal gradient. As you go down, it gets hotter, but not anomalously so. But then if you press two continents together, the tectonic force involved, the compressional force, is enough to have the rock undergo high pressure conditions at fairly moderate to low temperatures, nowhere near melting point. Normally, rock would not achieve high pressure conditions like that except in the mantle at much higher temperatures. So you get a wide range of different minerals forming as minerals from the Earth's surface are exposed to essentially a high pressure forge that will force them to recrystallize into different forms. We call this metamorphism. During an orogenic mountain belt forming event, we would call this regional metamorphism, because across an entire region of the crust, the compression of one crustal mass against another is driving geologic pressures very high inside the core of that mountain range. A very high-grade form of metamorphic rock, that is, rock that's been intensely compressed, is what we call gneiss, spelled G-N-E-I-S-S. And this is a very high-grade metamorphic rock. It's dense, it's hard. It was originally perhaps layered sediments, and you can see a layering in there that might be from that, or it might be from the minerals squeezed out into those shapes by the compression or the tensional forces that the rock is under. But the minerals are recrystallized, where normally you would have had maybe initially starting with a sediment with sand and feldspar grains, normal kind of beach sand you might think of, and at pressure, at temperature, in the mountain building event, the rock is squeezed into this form where maybe there are different kinds of feldspars, other kinds of minerals form. Where you had clay minerals originally, now you have mica, biotite, muscovite. Maybe even more bizarre, unusual minerals. Big gem-quality garnets and other things like that can be found in metamorphic rock that tends to produce very interesting, sometimes gemstone-quality minerals. During a mountain building event, the rock itself is altered. It's changed into other higher temperature mineral forms. The rock is physically twisted and folded. Slow, grinding forces applied over geologic time will change the rock and twist it into completely different shapes. And you get some very interesting structural geology out of mountain building events like this. Another example of a mountain building event of continental collision are the Alps, the Alpine Mountains of Europe, Switzerland and many other countries across the main belt of Europe. The Alps form a natural barrier and have played a major role in human history, but they are the result of a continent-continent collision, a mountain-building event that began about 300 million years ago when Eurasia and the African plate collided. And since then, they have been connected to each other, and tectonic forces sometimes grind them together again, and the Alps have risen episodically over time. Sometimes there's active mountain building, sometimes there's not. And when there is, there's more volcanic activity, there's more earthquake activity. And currently the mountain building is underway, and we see geologic activity in Europe as a result. The Alps are stunning, and I recommend anyone who has a chance to go there, especially if you go up to a place like Jungfraujoch, a high-altitude location here shown in Switzerland, where you literally go up to the mountain through a railway, a train that's been bored into the mountain like as if by dwarves. And then you emerge at the top into this structure, which is also a meteorological research station. And from there you can go hiking. But the panoramic view shows you the mountain splendor that you get when continents grind into each other, rising up into spectacular peaks that are growing faster than they're eroding, and therefore they can become so dramatic as they are. And in the geology of a mountain range like the Alps, you can see its history recorded. For example, at the Matterhorn, the iconic mountain peak on the border of Switzerland and Italy. It is made up of rock of two continents. The peak of the Matterhorn is made up of metamorphic rock that was originally part of the African crustal plate. Africa grinding up against Europe, a sliver of that African plate thrust up into part of the mountain peaks that form as a result of the collision. In the Matterhorn itself, physically, the peak is metamorphic rock from Africa. Below that is a slice of metamorphosed ocean crust. Remember, there was an ocean between those two continents when they slammed into each other. What happens to it? Well, most of it gets subducted, but slivers of it can be sharded off, can be broken off, and will become part of what is then forged up into high mountain peaks. This can happen, and the Matterhorn is an example of it. Below that metamorphosed ocean crust of that particular mountain is the basement rock of the Eurasian crust. African crust slammed up over Eurasian crust during the slow geologic violence of a mountain building event. Mountain building has been happening throughout the history of our planet, and the Appalachian Mountains in eastern North America are a wonderful example of that, and an example of how complicated Earth's geological history can be. The Appalachian Mountains are not one mountain range. They actually comprise several different mountain ranges that formed at different times as a result of different continental collisions. And then basically what we see today is the sum total of the history of all of those events combined. The Appalachian Mountains stretch from Alabama all the way up through Maine into Nova Scotia and on into Canada. The Appalachians began to grow, at least in their initial stages, as part of what we call the tectonic orogeny, the tectonic mountain building event. A volcanic island arc, a subduction-related island arc like Japan today, ran into, oriented as the continent is now, the eastern side of North America, although its orientation was different then. The tectonic island arc ran into North America and grew a mountain range. Later, an island microcontinent we call now Avalonia was driven into the eastern side, again, as it's oriented today, of North America, adding another mountain range and another piece of continental mass to the continent. When Avalonia ran into North America, it forged the Acadian orogeny, a mountain range that stretches through Maine up into Canada and formed a northern extension, essentially, of the Tectonic mountain range, which was a little bit further to the south. Later still, around 300 to about 250 million years ago, Africa collided with North America. This time, what is now eastern-facing coastline of North America was facing south, and the southern edge of North America ran into Africa, raising up the Appalachian Mountains during what's called the Alleghenian orogeny. At this point, the Appalachians were as tall as the Himalayas and formed an interior mountain range inside the middle of the Pangean supercontinent that began to break up in the Triassic period. Later, around 180 million years ago, Pangaea began to break apart, and with that, it formed the eastern and southern coasts of North America. At one time, the Appalachian Mountains were as high as Everest, but over time, they've eroded down, risen again, eroded down, and risen again, and eroded down. And what we're seeing today is the core of a very ancient complex of multiple orogenic events. The Appalachian Mountains are eroded down from what was their magnificent greatness maybe a couple hundred million years ago, but they're still pretty spectacular today and well worth a visit. I would recommend to anyone.